So, welcome to this video. Here in this video lecture, I am going to talk about tensors. A brief introduction, because these tensors are useful in the study of electrodynamics. So before moving towards tensors, let us revise briefly about scalars and vectors, because scalars are the special case of tensors of zero order, and vectors are also known as the tensors of first order, right? So first of all, let us talk about that. What are scalars? So scalar is a quantity, is a physical quantity, or a quantity is said to physical quantity is said to be scalar if that remained quantity that remained invariant under rotation of coordinate system and can be specified by a real number and these quantities having only magnitude. Only magnitude. And scalars are known as tensors of rank 0. Right? Now let us talk about vectors. So these are the quantities having both magnitude and direction. And these are also known as tensors of rank 1. And another thing which we have learned that these tensors, vectors can be expressed as covariant and contravariant form. As we know that a prime I, it must be equal to curly x prime I over curly xj and aj, and this is basically here the vector A is a contravariant vector. On the other hand, if I express a vector in this form and whose components are like this, curly xj over curly x prime I aj, that means the A vector which I am defining using these two components in different frame of references, then this A is known as covariant vector. So in other words, I can say that scalar and vectors are the scalars and vectors are the special case of tensors. Now let us talk about tensors. So first of all, I will talk about the mathematical definition of tensor, and then with the help of some example I will talk about it. So in mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to the vector space. Related to a vector space. So let us understand this definition with the help of some example. So let us take example from electricity and magnetism. So consider Ohm's law, and I am considering this Ohm's law in vector form. So current density is equal to sigma E. Here J is the current density, this sigma is the electrical conductivity, E is the applied field. So this equation is valid only in isotropic medium. Isotropic means it is a medium whose properties remain same in all directions. But if the medium is not isotropic, if we have to we are talking about an isotropic medium, then in different directions different current will flow. So that means now I am considering the anisotropic medium. So if I consider an isotropic medium, then current flow in different directions will be different. So to represent that, I can express it in this form. So sigma xx ex plus sigma xy ey and sigma xz ez, and jy, it can be written as sigma yx ex, sigma yy ey, and sigma yz ez, and jz, it can be written as sigma zx ex plus sigma zy over into Ey and sigma zz and Ez. So if I try to look at these equations, then here the conductivity tensor, so conductivity can be expressed as sigma xx, sigma xy, and sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, and sigma zz. So this is known as conductivity tensor. Known as conductivity tensor. Now, as I expressed the vectors as in the form of covariant and contravariant form, and where I have used the idea of partial derivative. For covariant and contravariant form of a vector, I have used the idea of partial derivative curly over curly x, like in this form, partial derivative form. So in the similar fashion, I can express tensor in the form of partial derivative. So in the same manner, I can define covariant and contravariant tensor of rank 2. So to define covariant, and contravariant tensor of rank 2, what I will do, there are three possibilities: A prime ij summation over kl, summation x prime I, summation xk into summation x prime j, summation xl akl. This is the one way to look at it. Then b prime I j, here I in the superscript and j in the subscript, again summation kl, summation x prime I over xk, and summation xl over summation x prime j, and b kl, right? This is subscript and this is superscript. There is another possibility. Summation kl and summation xk over summation x prime I, summation xl over summation x prime j, and ckl. So if I try to look at these two things, where we have taken the product of partial derivatives, and here this k and l equal to the rank of the two. So these are two indices, so that means it is a tensor of rank 2. These two indices will decide. It's a tensor of rank 2, right? So that means these all are the cases of rank of tensor of rank 2. And here both I and j, or in other words I can say that k and l are, both indices are contravariant. So that means this a kl, it is contravariant to both indices. But if I try to look at it, so it is a contravariant for this and covariant for J. Sorry, this is for the covariant, sorry, contravariant, and for this it is covariant. It means this BKL this is basically, this transforms contravariantly with respect to K and covariantly with respect to L. And similarly, I can say that CKL, it is a covariant with respect to both indices K and L. For both it is a covariant. So that means how in the covariant or contravariant form we will define the tensors, and these notations are useful in later study of the relativistic electrodynamics. So it's a very brief idea about the tensors in this lecture I have talked about. So thanks for watching this video.